Well, thanks for coming. I wasn't expecting, I mean, from the spreadsheet, I was expecting less people, which is great to see many more. So, just a quick introduction. Well, you are all familiar with what is the UK Acoustic Network, and the fact that 2 years ago we started this special interest group in spatial acoustics and immersive audio. We haven't done much yet. We've done a workshop, and we're going to probably do a conference after the summer. Actually, surely do a conference after the summer. But one of the ideas of this first in-person meeting is we've never had a meeting with the whole team, actually with the whole SIG. We have many more. I think we are, how many are we, Aidan? Probably 90 or 120? Many more.
90. 97.
97. But we wanted to do something in person and present, introduce to each other what we do, and possibly also discuss about what we want to do. We have some funding available for the next years, and we can decide what activities are worth doing or not. And in the meanwhile, also we'll have some people from Sonos as an industry partner who's going to tell us a bit more about what they do. So the day is going to work like this. We'll have a presentation from Sonos, which is the main one. Then we can have a tour. I can show you a bit of our lab. Then we can come back here and we'll have short presentation from the participants who agreed to do a presentation. If you're not in that list and want to give a presentation, please by all means do come here and do it. We won't be filming the Sonos presentation, but we will be filming the others. So if anyone is saying something that they don't want to be filmed, then please tell us and we won't film it, and we'll just put it on the UCAN website. And well, the first is Jake, who is now at Audio Scenic and not anymore at ISVR.
Yeah, as of a whole week.
A whole week.
Well, I think it was inevitable because I was still at ISVR when Audio Scenic didn't exist. But yeah, thanks everyone. So I'm just going to give you a little bit of a breakdown. Is it on? Oh, you press the record button.
Yeah, sorry.
A little bit of breakdown of who we are, Audio Scenic, what we're about, a little bit about our tech, and sort of what we're looking at doing over the next, currently doing over the next few years as well. So a little bit of breakdown of who we are. Back in 2017, we came out of a spin out of the ISVR, University of Southampton, out of Filippo Fazzi's team, along with work by Filippo and a guy called Marcus Simon, who probably quite a few of you here know both of them. And this particularly came out of some work as part of a project called S3A, which was quite a large joint project along with the University of Surrey, University of Salford and BBC, and that was looking at what's the future of particularly spatial audio reproduction, particularly for a home environment. And in terms of the ISVR area of that research, a lot of tech that came out of that was a lot of advancements in spatial audio reproduction over loudspeakers, but particularly dynamic approaches. So things that we call user-centered 3D audio, or ways that we can adaptively and dynamically adapt audio reproduction based on the preferences of the user. So a little intro to the team. We properly kicked off about 3.5, 4 years ago. We've recently grown quite a bit. We're predominantly based down in Southampton, which is where a lot of our engineering and R&D guys still are, but we've also got representatives across the globe, particularly working with our OEM guys. So what is our technology? The approach of the Audio Scenic technology is to employ computer vision tracking to track positions of one or multiple listeners, and then create beams of audio, often using some form of loudspeaker arrays, sending beams exactly to where the left and the right ears of the listeners are. Once we have this done, and we have the pressure controlled exactly at the user's ears, we can actually make it sound like whatever we want. We can send them direct binaural audio. We effectively have a pair of virtual headphones controlled at their ears, so we can reproduce 3D audio without the need for speakers all around you. Or we can do things like separate sound zones for multiple listeners. Lag here, sorry. So this is a little example of what that might look like in practice. It's going to play. So in this case, we've got a soundbar situated in front of the listener. We've got a little webcam situated in the soundbar. We're tracking the position of the listener in real time and adapt the changes in the positions of these beams that we send to the listener to ensure that no matter where they move throughout the room, we're always controlling the pressure exactly at their ears. And in doing so, we can reproduce, say in this content, a teleconference call or any form of upmix, multi-channel or binaural, without the need of having speakers all around the listener. This isn't just restrictive to a single listener. our tech is also adaptive to multiple scenarios. So in this case, maybe we begin with a single listener, but then we detect there's a second person that comes in. So the system can automatically detect that, track both users, and send beams to each listener. And then maybe the scenario becomes a bit of a party, and 10 people, it's not really feasible to beam exactly to all those positions. So we initiate some other room mode, which is more about an immersive room fitting beamforming mode as well. So there's two key issues that Audio-Scenic tech has solved, and the first one we've just been chatting about, and that is the issue of sweet spot. So basically, almost every form of spatial audio reproduction over loudspeakers is always restricted to a specific sweet spot. There's always one place where the reproduction actually works. If you go into the maths of the theories, they often assume the listener is in the centre of some uniform array, depending on the approach. So what we're doing is adaptively changing that sweet spot in real time based off of our computer vision input. This is a particular issue for inverse filtering approaches as well. Another key issue is, particularly if you're looking at inverse filtering, this is a really significant computational load. So actually doing this in real time, dynamically adapting that to the user positions is really significant and not applicable for embedded devices. So on here we've got a little indication of operations or computational load. In orange here we've got a standard inverse filtering approach that dynamically adapts as you vary the number of speakers. Obviously the load goes up. And in green you have the virtual approach, which is what we employ for our beamforming, and the computational load is considerably reduced. So that means we can actually make real products that do this in real time that don't require a very big expensive computer to run. So let's go through a couple of use cases, some things that we're looking at, and hopeful products that we're going to be bringing out soon. Well, this actually is our first product. We released this at CES earlier this year in conjunction with Razer, the Leviathan 2 V2 Pro. Lorenzo's got one, so dare I say Lorenzo
if anyone wants to demo it, it's here. It's on my desk.
Fantastic. Or if you'd like a demo, just have a chat with me afterwards and we can arrange that. We're really proud of it. It won 12 Best in Show awards at CES this year. And just a couple of some of the reviews. Probably my favourite is maybe unspeakable. So you can see this is a 5-channel soundbar with a webcam, and it's specifically designed for gaming audio. So gamers sitting in front of a computer. Normally they're wearing a pair of headphones. Sometimes people set up a surround sound system, but more often than not, people just mostly using headphones. And we're freeing the user from a headphone scenario here. So we've got a couple of different modes. The most interesting one being the fact that most game engines are delivering really decent binaural audio output. So it's a really great application straight off the bat. And we're hoping to continue on with the gaming soundbars as well. We're also looking at implementing this more for laptops. Obviously, a laptop, you always pretty much have a webcam there. So we've already got a tracking solution there. This is a bit of a mixture depending on what we have available to us in terms of loudspeakers. We can do this directly with the standard stereo loudspeakers that are already there, but as we always know in spatial audio, the more speakers the better. So we're also looking at more innovative designs such as these sort of prototypes here where you actually put in a small array built into the laptop. Home cinema, this is really the core of what we do. This is what really drove Martin Filippo early on when they were doing this initial research, and has been really at the core of one of our interest areas since then. Home cinema is a perfect environment because the vast majority of people no longer have surround sound systems. They're mostly buying a soundbar. So the idea here is, can we get a product which works not just for a single person, but multiple people at the same time, adaptive to whatever environment it's being put into. Obviously that's not without its challenges, some of which has been touched on by in our previous talk. This is a key area that we're hoping to get a product out in soon. And also looking more in terms of personalised private sound zones. So teleconferencing is certainly here to stay now after the last few years, but most places, most things like Zoom and Teams, sometimes it's stereo audio, mostly it's mono. You can get a binaural mix in teleconferencing. The fatigue on the person is massively reduced because you can have a much more natural mix of speakers separated in space with a bit of ambience, much more natural. So we're also looking at employing this tech into soundbars that obviously accept this binaural input for teleconferencing, but also create more of a sound bubble for that specific user. So if you imagine sort of an open office space, the hope would be you could have a sound bar in front of that person, and the desk next door wouldn't be too disturbed by your conference call. And how can we do that? Well, this is all about loudspeaker beamforming, right? So we can control your pressure exactly where it is, or we can send more like mono beams in different positions. So this is just a little example of one of our arrays trying to output to the area that's dashed in green here. So this is where our office user is having his conference call, but then this is where the person sat next door to them in purple. So we're steering in null and trying to minimise output in that direction as well. As I said, it's always better to have more loudspeakers, but we can configure this and work within any limitations of any array design. I did have a little video, but just to demonstrate this of a prototype that we have, but the audio isn't working, so if you want to hear this, maybe I can show it to you later, because my laptop speakers are not very good. And also, personalised sound zones are really applicable in particular to the automotive industry. So the idea here is we've got maybe parents in the front and kids in the back, and we want to create 4 separate sound zones so they can each listen to different content. So kids in the back can play a game or watch a movie and not be disturbed by, or rather the driver can not be disturbed by that, whilst they have more driver awareness cues such as sat nav or positional awareness. Cars coming on your left, you can hear it coming up on your left, and maybe the passenger can listen to a phone call at the same time. And we've also developed a whole suite of tuning tools to go along with the tech. So with a lot of our HDK kits and soundbars, we're working directly with the manufacturers and also the brands to create a set of tuning tools which they can use to help uses our internal framework and our software, but allows them to tweak the soundbar in whatever way they want. So things like standard audio processing, EQ dynamics, but also things like HRTF selection and more spatial properties. So I'll just wrap up with what our vision is, and that is we want to be the enabling technology behind personalised immersive audio reproduction and offer a revolutionary listening experience in a multitude of normal everyday situations, but without the need for headphones. So thanks for listening. I'm very happy to chat to anyone, or if you're interested in arranging a demo or haven't listened to a soundbar, please do come and catch me afterwards and we can arrange that. Thank you.
So I bought the soundbar and I'm very happy about it. As you know, because we've discussed it in the past, there is one issue which is unfortunately rather major for a lot of the work we do here with the current available technologies that use loudspeaker-based binaural audio, which is head rotations.
Yep.
A lot of the work we do involve perceptual training where massive head rotations are fostered. I mean, we ask that people, we try for people to rotate their head as much as they can. Do you think, I mean, I know that it is possible to have maybe a couple, 2 or 3 sound bars around you, at least the front, and allow for this. Is there going to be anything out soon?
We can certainly handle head rotation within the beamform. The issue we're finding is you really need to not just have the head rotation on the reproduction side, the loudspeaker array, you need the head rotation in your initial binaural encoder stage as well. Mm-hmm. So currently so far, we've sort of, particularly the Razor soundbar, just assuming we've got a gaming situation, we don't have access to that binaural encoding. The engine is doing that. There's no way we're going to get access to that. So that's sort of off limits for us. That's not necessarily the case in other scenarios, such as the home cinema area. So that's something I'm actively actually looking at for future products. But it's a little bit application specific, as I said, because for that to really work well, you need access to that encoding stage, which is something we're looking at doing and having our own encoder as well, including some of this, for sure.
But yeah, for example, with the Razor one, if I could pair 2 of them and put them a bit of like V-shape like this, and at least have this sort of level, then anyway, I'm taking care of the binaural rendering.
But okay, in terms of just purely the array side of reproduction, for assuming most scenarios you actually are very rarely turning all the way around, you're sort of almost always looking at a screen in a lot of these applications.
Yeah,
so the head rotation you can often assume is very limited. We can do that with one soundbar. You don't need.
Yeah, no, absolutely.
If you maybe want to do full 360, in fact, as a research project we did about 4 years ago, the ISVR, where we actually did that. We got 4 arrays in the quad, and we got a VR headset and did exactly that. Yeah, maybe that might be advantageous there. Yeah. But no, we can do it. It's sort of, plus or minus 30 degrees looking at the screen. That's totally possible.
With a larger.
Even with the Razer size. I mean, it's always larger arrays, always better for low frequencies, right? But even with the Razer size. Cool.
Brilliant.
All right, thank you very much.
Next we have Johan.
All right, hello everyone. I am Johan, and I will give you a short introduction to what kind of relevant research is currently going on at the Imperial University of London, which, in case you do not know, has its main campus in Mile End, which is East London. It's not that far east as people might think. It's not as far as Canary Wharf. It's definitely not as far as Stratford. You can actually walk from Brick Lane, which is typically where most people's mental end of London ends. Brick Lane, well, you can walk just a bit further east. It's not that scary as you might think. So yeah, this is our nice building, the one that figures on the pictures. But I think the reason why I'm at Imperial University is because it's hosting the Center for Digital Music, or C4DM as we usually call it, which is of a size that size where you stop counting of how many people are exactly involved in it, but I just counted roughly 11 core academics and then a handful of people that are maybe not primarily affiliated with the center, but for instance supervise some of our students or the other way around. So people keep on going and leaving. So we have a ton of PhD students. Again, that amount where you stop counting becomes hard. Just yesterday evening I went to a table that is definitely out of date, counted 73 out of them. These days most of them are supplied by the Center for Doctoral Training that we are hosting, which is starting its 5th year next September, and that is on the topic of AI and music. So obviously it's main part where our research is focused. So intersection of AI and music can be in kind of the broad definition. So music can be audio, can even be I think the majority is audio. Some people are mostly focusing on kind of symbolic domain, can be even user data like graphs of user interactions, things data you have a lot at Spotify, things like that, to more the core DSP part, what is audio. I'd say the majority of people are doing things that are more related to what we call music information retrieval, which is we have an audio file and we try to get some sort of musical characteristic out of there. Can be many things, can be very musicological things like what is the notes, whether the chords, the keys are being played, to something that is maybe a bit more accessible to non-musicians. What is the genre, what is the emotion you can get out there, what is the tempo that's in there. So that I'd say is a large part of things that we're doing. So yeah, as I said, ton of PhD students these days. I did say too few postdocs. That is something we're currently lacking. So I'd rather have more, or a bit more balance, but there is just due to funding not really there. Then about me, so currently I'm a lecturer there. My own background is a kind of mixed background in electronic engineering, multimedia, DSP. Back in the day when multimedia still was a hip word, and then AI back in the day, it was still a very different field than it is today. And my own, just this to illustrate that my own background might be a bit different than the background of some of you here, because the main point I want to make is I'm not an acoustician, I'm not an audio engineer, so there's definitely areas of expertise that I am lacking, but then on the other hand I hope to be complementary in all sorts. So my own PhD was very much music information retrieval focused. To give the example, in my case I wanted to find chords and keys out of recorded audio. And that is where the main body of my own research career was until a couple of years ago, when I then slowly got a bit more into spatial audio. Most notably, until a year ago, I was a research fellow here. I still notice I am on a large part of the promotional material, which makes me very happy. Aidan and me, the cover guys of those material. Where I was working on that Sonicon project, I think Lorenzo will mention that for sure, and I'm still sort of sideways involved, contributing when I have a bit of time to do that. So specifically, my interest in spatial audio research, so as I said, I'm not the fully fledged audio researcher, or neither am I intending to start a group that can compete in breadth, let's say, with Imperial or York. But I think I find myself in the luxury position where I can just say, oh, this is a particular area of interest that I want to work a bit on, and then if I run into problems, parts that I do not understand, I can come to Lorenzo and say, can you give me a bit of background that I'm lacking in a particular area? So typically the way I try to approach things is based from my background. I would say music information theory is a bit more mature in terms of applying machine learning to audio research. So I think that is the things I can bring. So specifically, I know nothing about room acoustics, things like that. It's not that I would not want to know about it if I could just take a pill and learn about it. But I think it does not make sense for me to spend a lot of time now to become 80% as knowledgeable in the field. I think it's better if I stay focused on what I actually can, and then what I can hopefully be complementary with someone else. So this is also sort of an open call for potential collaborations. So what actually do I slowly get a bit of expertise in, I hope, is binaural audio. Mostly looking at personalization of binaural audio, and more specifically in how can machine learning help in sort of optimizing certain workflows that are there. So there is, in kind of the spatial audio domain, my main research interest, and I'm also interested, based on previous work, in everything that's browser-based. So browser-based VR and AR. More specifically, I'm looking at using the 3.js toolkit. I'd say the big alternative that you might have heard of is Babylon.js, which is something I'm not using personally, but it's kind of it's basically, if you want to do any work there, you choose, you want to go 3.js or you want to go Babylon.js. Went with 3.js for not that many reasons. The other options apply, basically. And group, as I say, is basically talking about myself, and what I'm currently exploring this research with is mostly with bachelor and master students that are doing their project in a VR project with me. I do PhD supervision, currently not doing any spatial audio related topics on PhD level because a couple of simple reasons. One is funding. Most of our PhD students get funded, especially now on this music and AI part. Also partly of just want to get a bit more experience before I feel confident enough I can handle bachelor and master level projects in spatial audio. I feel I can contribute something. I'm not sure yet if I can on my own supervise a PhD project in this particular topic. Although there are some PhD students, so as I said, there are at least 10 other academics that do a bit. So nobody's actually focusing on spatial audio. There is no core working group on spatial audio, but occasionally there's, we have Josh Rice, who used to be up until last year the president of the AES, who occasionally gets a PhD student that does a bit of spatial audio. I believe Sonos is actually sponsoring one of them. So there is no one academic that kind of attracts all the spatial audio research, but I do hope at least to have a little contribution in my subfield of the part I understand. At for now, binaural audio, and mostly special personalization of HRTFs. So then, what are some of the things that I'd like to share with you today? So the first thing I'd like to talk about, and basically just mention, because I tried to keep this short, is that I have a paper accepted at ICAS, which will be presented in June, that is, with Lorenzo, and basically with the given introduction should not come as a surprise that I'm interested in kind of data-driven research methods to HRTFs. So one thing that basically maybe with my naive approach wants to know about, okay, there are many different measurement setups. There's still the one here in Imperial. There are other collections. If you say data-driven, you want to use as many data points as possible. So can we in some way combine the given different setups and what is necessary to just take our data from Imperial, from Sonicom, and combine them with other measurement setups? Can we just join them and then just naively throw them into machine learning algorithm and then say more data leads to better performance? Long story short, I think that is unfortunately not the case. I do have the next slide, depending on time, if we can go in there or not. Let's move on to the next. So that was all, this kind of was sort of the practical study aspect that in order to make that study possible, I've been developing a particular toolkit that I think will come in very handy for anyone who wants to combine kind of different HRTF measurement data, specifically with a focus with machine learning. So it is currently submitted for the AS conference in spatial immersive audio. So that's why I say there's a public release that will be happening in August. Currently, it's sort of internal testing. Also propose a tutorial. So if everything goes well, I get a bit more time to talk about that, and then hopefully you will hear about it in the relatively near future. Other kind of random things thrown out there, working in progress, that basically looking for someone to say, hey, that sounds interesting, maybe we can get a conversation started about this. Just for my own use, I wrapped the 3DTI toolkit, which was a previous project with the University of Malaga, and again Imperial College, where they built a binaural renderer, among many things. I just wanted it to run in Python just because my workflow did not exist. I did not find any decent Python-based renderer, binaural renderer, so I just wrapped this existing toolkit, which is C++. Currently it's working on my computer, and it's at a stage where I basically need at least one person to express interest to give me the motivation to wrap it up. Maybe needs a day work, but I just need the motivation. Someone saying, I want to work, use it too, and then I'll put in the extra day of work where I can then share it. So kind of very, very practical offering. And then some of the nice things that I can now take credit for, of some of my students doing things. Finally at the stage of my life where I can take credit for other people's work. So this is actually a bachelor student of mine who's submitting this as his project next week, so it is quite mature. Let me get this on the screen. Here we go. So the title of this project was Specialization as a Service, and the idea it kind of does rendering of spatial audio for people who do not necessarily have the technical skills, but can just use it as a web service. So it has actually quite a nice introduction, which you can read, but which you won't definitely not need. but the idea is you can just upload an audio file. What it then does, it separates this into a couple of different stems. So this uses source separation in the background. Send it off to the server. Then what's then going to happen, it's going to separate it into different stems, render this in a web app where you can then sort of do a basic spatial mix of the different components, which is bass, drums, vocals, and then the rest, the clearly harmonic components. I have noticed it does not necessarily always work from the first time, so let's demo effect. The thing is, I never know how long to wait before giving up, so let's give this a couple of minutes. There we go, and we can get this orientation where now we can start. It is probably pretty bad, or even non-existent audio. Then the idea that people just can play around. We have here visual representation of where in the space. A bit exaggerated. This is in meter. Have a look around where exactly in space do we position everything. Kind of play around this, get a sort of more spatialized mix. Very unbalanced right now. You can actually hear things you would not hear in the full mix. You can just the vocals. And so this is kind of preview using Web Audio API, but you can actually render it high quality, and again uses the 3D TI toolkit, which renders it on the server, and then could not get this done for this particular version, but hopefully then upload your own HRTF, so you can render it specifically for your own use. Suppose you came here to get your HRTF measured. That is one of the fun things you can play around with them. And then the spatial rendering, which obviously kind of went a bit too extreme with the parameters. Everything's too distant, but you get the idea. So other work being planned, so these are two of my master students who will work with me over the summer, so this is mostly planned work, just to give you an idea of things we're going to do. So with Jared, we plan to do kind of machine learning based iterative personalization based on image and anthropomorphic data. Kind of, since it's a master project, kind of the idea is to get it to replication of currently existing work, not necessarily improve that, but hopefully that can be a starting point for maybe future research. And then with Kaiwei, we plan to do creation again in 3GS of some sort of bare bones measurement setup of localization test, again as a kind of a springboard to hopefully getting more complete tool chain ready that maybe can improve with future projects with future students as well. So then, since I have time, we don't necessarily need to stick to the 10 minutes. I can give you a very short overview of this is particularly the ICAS paper, where the idea is can we use machine learning to find out if there are actually replicable measurements, replicably identifiable differences between HRTF measurement setups. So the main idea was, or the motivation for this work was kind of the relevance of machine learning, because we know if you want to use any type of machine learning algorithm, it's always going to go for the easy win. So meaning that if a machine learning algorithm can take some data that is maybe not interesting for humans to try to distinguish between HRTF measurement setups, then it's definitely going to take that easy route. And indeed, for that, I set up an experiment. I just took a lot of HRTFs collected in different places. I was wondering, can you actually reliably recognize where this particular HRTF was measured? Because if you think about it, the HRTF should be about the human, not about the place where it was measured. But kind of, unfortunately, it proved to be trivially easy to find which actually where it was, where was it measured, and then more interestingly, the question was how does it figure out where it was measured, and then just did a bit of analysis of which of the frequencies do contribute to this identification. And we see here kind of particularly in the low end, which probably would mean some sort of typical room reflections that are present in one location that are not present in the other location, sort of will act as a fingerprint for that particular measurement setup. You can see the same thing in the very high noise data, very high frequency data, which basically is noise for the HRTF. That noise is in a way consistent, so it can act as a sort of a fingerprint of where it's actually measured. And it seems to be quite robust, because I experimented a bit with having different frequency ranges. So this is kind of the full frequency range, and then it's can get it's massively high classification accuracy, meaning that so I think I used 10 different data sets, and then took I already forgot the numbers, something like 20 different HRTFs, 20 different people, and in 98% I could actually identify where it was measured if I took the whole spectrum. And even if you say, okay, maybe we can cut off the DC offset, so the DC offset quite predictably is a very good indication where it was measured. On the other hand, if you then cut off these noisy ranges which you will not use, still a more usable range, you still have 92% of the time you can reliably identify where something was measured. And even if you go a bit more aggressive in the removal, so you could argue maybe above 15 kilohertz we do not really need the type of data. People cannot hear that high anymore if they've had a couple of years of experience with music. But even if you just remove all the potentially identifying information above 15 kilohertz, you can see there's still a lot of sort of a fingerprint that is reliable to identify what is the actual measurement room, measurement setup that the HRTF was taken. And obviously you can get rid of everything above 15 kilohertz because it's not really useful, but you cannot really get rid of or just simply chopping everything below. Let's say you would need to get at least chop off everything below 2000 hertz. By that time you don't really have a useful HRTF anymore. And that work is something I kind of want to continue just to get a bit more insight of what actually makes kind of what's the exact kind of fingerprint that's available in the data, and then ideally in some way can we figure out some post-processing step that gets rid of these these unwanted measurement-specific data, and that hopefully would lead to a way to be able to more reliably measure HRTFs and then make them a bit more useful for any type of machine learning setup. So the long and short of that is available in ICASP. I think papers are not published yet, but there's a preprint available on archive, or just ask me for the final version. I'll happily send it to you. And this is a bit about the work that I submitted to the AS Audio Conference. This is just a small illustration with the setup, the toolbox I've been using. And so it's meant to interact seamlessly with all the major machine learning toolkits. Notably, I've tested with scikit-learn, which you can see here, PyTorch and TensorFlow. And the idea is once you, this is basically the functionality I provide, just a simple one-liner where you can just say, load me data set where as the features I want the H ears in the time domain, use both ears, but the right one is mirrored, so it becomes another left ear, and my labels are going to be the sides, and just to see, can you actually distinguish if you mirror a right ear to become another left ear, is actually a valid approach to test to increase the number of data points, meaning that they should not be separable by a machine learning algorithm. And indeed, when I tested this, I got 50% chance level of recognition of separating the left ears from the mirrored right ears. But the main point here is that this couple of lines is already an experiment setup. It's mostly kind of the illustration of the elegance of scikit-learn in this case, but this just gives you a pipeline where you can check a couple of different setups. So what this does, this basically compares providing the H ears in the time domain versus the magnitude domain, and then adds or removes PCA either with a reduced number of components or all of the components. And this just tries all the different combinations together with a linear SVM and just gives it results. And obviously, in this case, I actually wanted the algorithm to fail. I wanted it to get to the 50% chance level of detection, and indeed that was the case. But a very similar setup is what I used for the ICASP paper, where I was hoping to get a chance level of detection of the measurement setup, but as you could see, it was the high 90s. And since I used, I think, 10 different setups, chance level would have been 1 in 10, so that was quite a strong indication that there is something in that measurement data that ideally should not be there.
Sorry, can I don't mean to be, but if we could move to the next speaker. How long do we have?
No, this was the end.
Okay.
It was the end. So,
no, nothing but well beyond.
Yeah, sure, I'm mistaken. Then kind of the end I want to mention here. So one of the nice things about QMR is that we have kind of the full range of schools. We also have a School of English and Drama, a School of Languages, Linguistics and Film. Just did a massive renovation and have new facilities where they have now a kind of 50-seat 4K cinema with Dolby Atmos, which will sort of a bit involved that we can use this space occasionally. So I was just proposing maybe for a future meeting we can, if anyone figures out a good reason to use a 50-seat setup with Dolby Atmos. I was going to propose having the sort of a listening party for the 3D spatial audio competition, which we did here 2 years ago. Unfortunately, I checked yesterday the date, and I will be at the conference on that same day, so I cannot host you at that date. But if any one of you thinks of a way or a reason why you want to come together with some people listening to a Dolby Atmos setup, I'll be happy to host you there. And that was the end of my presentation.
Sorry for interrupting, but yeah, I think we still have other 3 presentations, and I'm sure people will intervene eventually. Yeah.
Hey, nice. Okay. So thanks, Lorenzo, for inviting me today. This is really great to meet all you folks. So I'm Gavin Carney. I'm from the University of York, from the Audio Lab at the School of Physics, Engineering and Technology. I was interested to hear on the way over to your lab facility here, somebody mentioned the word Thunderdome. That's also the affectionate name we've given to our 50-channel loudspeaker system. I don't know if it's something to do, with spatial audio people on Mad Max or wherever. So as you can tell from this picture, a lot of the work that we do here is based in and around virtual and augmented reality and immersive audio for virtual and augmented reality. We've had particular success in this domain over the last few years. I'm sure many of you have heard of the SAIG filters that we measured at our lab that got integrated into the Google Resonance pipeline. So it's kind of nice when you go to play Epic Games Fortnite, for example, you're listening through the Yorkshire ears. So it's really kind of cool thing to say. And our team consists of about 30 or so researchers, academics, postdocs, PhDs, and we have various different topics of audio technology that we research within the lab, but immersive audio permeates pretty much everything that we do. It's definitely a passion for our lab, and I'm sure you recognize some familiar faces up here. I hope you do. What I wanted to do really was just kind of touch on some of the portfolio projects that we have in our lab, keep it quite high level, but if you have any questions as I go through this, please go ahead and answer them. Sorry, I'll answer them. You go ahead and ask. The first thing that I wanted to touch on, which is kind of quite an important research topic for us over the last few years, is musical interaction in the metaverse. So we've been doing a lot of work, particularly post-pandemic, to try to bring people together, musicians together in shared virtual immersive environments. I think we can all appreciate, having been through the pandemic, and those of you who tried to do any musical performance over Zoom, it's pretty bad, right? You just cannot do it. And so we're very interested in not only low latency systems where you can bring musicians together into a shared environment, for that environment to be realistic and for it to be immersive, and to try to do things perhaps in a shared virtual immersive environment that you can't do in reality. And of course, this sort of thing also creates a level of accessibility for people who couldn't normally enjoy, for example, going to a recording studio for whatever reason. So some of the work that we've done has revolved around our collaborations with the BBC. Recently, we went to the BBC Maida Vale studios. Sadly, Maida Vale is closing down. I'm sure some of you heard of this. But we managed to spend some time in Maida Vale and to try to mock up a virtual rendering of one of their really important studios, Studio 4 in Maida Vale. In fact, we spent several weekends mapping the entire acoustic facility. I wish somebody from Guinness was there, because if you take, including the eigenmic impulse responses, which is like 32 impulse responses measured at once, we measured over 80,000 impulse responses across the studios in Maida Vale. And so when they say, when you die, you're going to see your light flashing before your eyes. When I die, I'm going to hear a long sine sweep. Right? But suffice to say that we managed to measure frameworks that would enable 6 degrees of freedom VR rendering. And we built a system that allowed remote performers to dial into a virtual version of Maida Vale, to be able to move through the space and experience the space as they would acoustically in reality, and of course to have a fully virtual reality complementary visual to go with that. So the goal with this was to try to see if you can create commercial quality acoustic recordings live performance recordings in a virtual version of real performance space. And I'm really happy to say that it is actually possible. This is just an example of, it doesn't matter about the audio so much, but it's just an example of some of the research that we have had done with several performers who come into our lab and tried out this experience to see whether or not they can actually go ahead and do an actual physical recording within the virtual reality space. And it's really interesting to see the behaviors within VR, what works for certain people, what doesn't work for certain people. Of course, if you're in a VR space, you still need to see your instrument, right? And so this experience has pass-through mode where you can map around your instrument and still see that in real life. Of course, you're at the mercy of the quality of virtual reality headsets and their pass-through modes. I think this picture here is from the Quest 2s. The Quest Pros are a little bit better, but it's improving. Well, suffice to say that we like to run control experiments in these sort of virtual performance environments to see what are the thresholds here. So if we're getting people to interact with each other and we start changing acoustical properties of the space, make it more reverberant, or if we start to change the latency conditions, what can we get away with? And typically, you're talking about 30 milliseconds or so before, in terms of latency, before it starts to become noticeable. Click tracks really help with all of this. So that's ongoing work, and this is just kind of one application. The virtual recording studio side of it is one application. We've also done recent research where we've gone into the musical education realm. We had Jamie Cullum and Milton Keynes teaching kids in Reading and Suffolk over a UK-wide immersive networked experience, and that worked really well, and it was very natural and very plausible. So there's lots of experiments to do in this space, particularly if you're going to put on virtual performance, virtual concerts. So can you get an audience interacting with the performers, or if you have performers in very remote locations, could you have a real audience watching one set of performers, another audience watching the other set of performers, and then having augmented reality characters or avatars representing the other performers from the other locations, and how would all of that work? What are the frameworks involved? So lots of exciting stuff to happen there. I'd be remiss to give a presentation on our work without talking about some binaural stuff. So this is some work that one of my colleagues, a PhD student who's just finished, who Lorenzo examined, thanks Lorenzo, Benjamin Swede, has been doing. And I was very happy to hear in the last presentation work being done on machine learning for HRTF processing. One of the big problems, of course, is you need data to be able to train these networks, and there's not a lot out there if you kind of consider the amount of data that you need. Ben did some work in consolidating all of the existing HRTF databases that are out there, and it still wasn't enough to properly train some machine learning models. So what we've done is we teamed up with our colleagues in computer science who have what's called a universal head model, and this is basically derived from scans which were done, actually some of them were done at Imperial, some of them were done at York, and some were done at Liverpool, to create a morphable model that you can change the shape of the head, change the shape of the ears, and from that you can use mesh to HRTF to create a new set of realistic binaural filters. And so we're currently in the process of creating what's known as the Hummingbird database, and we have generated 5,860 HRTF data sets so far. Our aim is to try and get to 10,000, but this takes quite a lot of our university's computing power, so we're not so popular with certain camps in the university for taking up all of the bandwidth. So, but we do hope to have something released later this year. Another fun project which is actually funded by UCAN, so I thought I'd better mention this today, is called Binaural Acoustic Responsive Canines, or BARC for short. And for those of you who know Lauren Ward, this is her dog, Marco, who's really kind of become a mascot in the lab because we see him around so much. But he's a guide dog. And what we really wanted to do was to see whether or not there's ways in which we can help with the training of guide dogs using immersive audio. And so in order to do that, we need to really get more understanding about the spatial hearing in dogs. And actually, if you look at the literature, there's not a lot out there. We know some of the physiology is similar in terms of the working of the inner ear, but certainly, of course, the outer ear is very radically different. And so, yes, we do want to measure HRTFs of dogs, but we also want to try to do some scanning of dogs' heads as well. So we do have collaborations going with local vets and so forth to help us when dogs are being worked on, and maybe they're just they're just being asleep. We can non-intrusively take scans of their heads. But measuring the HRTFs themselves is actually a problem, and so we're also looking at ways in which we can track the heads of canines in an adaptive way, so we can measure the HRTFs and think of a rig that we can just put over the head and not to be too invasive for the dogs. So that's a fun ongoing project. Another project that we're working on this is actually its second iteration of funding. This is called Enhanced Audio Description. So if you're a visually impaired person and you go to the cinema, you typically are given a set of headphones and you are listening to a third-person description of what's happening on the screen. And this can be, quite disengaging. It's a very useful service, of course, but it can be quite disengaging, and sometimes you don't follow exactly what's happening on the screen. Even to the extent that you're talking about these days Dolby Atmos mixes, right? That could be folded down, even if they're in binaural. You're typically talking about sound design strategies where all of the Foley and all of the character-driven sound effects is coming center channel. And we've done experiments with visually impaired people where we've literally asked them in a scene how many people are talking in this scene. No overlap dialogue, just one after another in the scene, and the error rate drops significantly when you start to spatialize away from the center channel. And so the Enhancing Audio Description project is about taking object-based audio, repurposing it into a theatrical mix that lessens the need for the audio description. So that's in its second round of funding. We found it interesting, actually, when we showcased this, some of our test movies to both visually and non-visually impaired people, normal sight people and visually impaired people. And we found that that visually impaired people, they liked it. They thought it was a great alternative to soundtrack reproduction and a great alternative to standard audio description. The people with normal sight found it fantastic, and they thought this was an amazing, different representation of the soundtrack, and they really wanted to have more of it. So now we're actually looking to loudspeaker methods and to try to understand what works and what doesn't for a distributed audience. So if I actually do start to do things like spatialize sound effects and dialogue away from where it's seen on screen for a distributed audience, how much can you get away with in terms of ventriloquist effect? When does it become annoying? And do you still get that same perception of immersion that you would get if you're listening on headphones? So fun stuff ahead. Another project that we're working on is one called Sound Fields, and this project is aimed for kids who have autism, and particularly those kids who have auditory hypersensitivities. So some kids go into particular school environments, or maybe there's the sound of babies crying, and they just can't stand those sounds at those environments, and it's very difficult for them. And so we've been working with these children to try to create an intervention therapy framework whereby we have a VR game, and the idea is that we use binaural-based spatial audio to create realistic immersive sound fields that expose them in a very controlled manner to those problematic stimuli. And so that over the course of an intervention period, they get a better therapy, and we've shown that actually there is statistically significant difference between doing this in full immersive 3D audio than over just standard stereo. Okay. That's really it. So there's lots more. If you want to go to the Audiolab website, check out everything that we're doing. You know, I'm scratching the surface here and just some of the projects within 10 minutes. But yeah, we do work on voice science and environmental acoustics, health and well-being, and of course immersive audio. And do follow us on LinkedIn and Twitter as well, so check out what we're doing. Okay, any questions? No? Yeah?
Just on the topic of dogs. There's quite a lot of different dog shapes, dog head shapes, and dog ear shapes. What do you plan to do to remedy that?
It's a great question. I mean, so yeah. I mean, we're going to start off with guide dogs because, you know, they're kind of our target at the moment. But I think it would be good to try to understand the physiology and how that impacts on the HRTFs to get a feeling for, you know, what parts of the spectrum that really kind of radically could change. I mean, and I feel it would radically change the difference between a guide dog and, for example, an Alsatian in terms of the outer ear structure is massively different. So particularly at, you know, above 2K, you know, it's going to be quite a different response. So what do we plan to do? Yeah, we plan to try to do scans and HRTF measurements. But we'll see what we can achieve within the time frame of this project, which I think runs for another 6 months, and then hopefully we can get further funding. So, any other questions? Okay.
Just so it's not a question, but it's some potential follow-up would be great when you launch the Hummingbird to then link in the Johan's framework, so that we can also use it. And on the dogs, I'll tell you a bit later about what you know about the using super resolution GANs for upsampling HRTS, because it might be that you can't really take full HRTS.
Yeah, I know. I imagine the data will be quite noisy, and that's the signal processing challenge here is one of trying to do adaptive HRTF measurements under, you know, probably very movable receiver positions. So
probably unreadable methods is simple as that.
Okay, thanks everybody.
We have our final 2 presentations.
Right. So I think I'm a bit out of place here, but I think I think I hope you find some connection. So my name is Merit Baraket. I'm an architect by training. I mostly am interested in computational architecture. A lot of people heard of computational acoustics. It's actually architecture. But I use it to try to bring in perceptual aspects and into the design flow of a designer and architecture in general. So just a little bit of background about architecture. We don't know anything about sound unless you are trained as a musician or trained as an engineer, nothing. So I was trained as a musician and also just generally a geek. That is the reason why I'm in that field. And part of what I'm doing is it's an evil plan to tell architects you need to design for sound. And by doing that is just, you know, talking to students and like whispering in their ears and talking to other people and whispering in their ears and working with them. And so, when we think that if it's a good design, you can get people to move in the space the way that you want them to move. Obviously, most architects just think visually, and they don't look at the architectural or the acoustic sound. And so, part of the computational side is that we look at, you know, biomimicry and adaptive systems, and bringing in the social cohesion and the spatial social sciences into that. And so, what I'm trying to do is that it's focus on the sound side of that. And see if we can come up with computational models for designers. So my entrance was I taught myself essentially what I could from the depth of knowledge that you have. I have like a little bit, but I made an agent-based system tool for architects to understand psychoacoustics and bring it into the design flow. So mostly if you've ever been into a space that's been designed, it looks amazing, and then you just sit there and you can't hear. And so the idea is, okay, telling the architect, okay, this is the space, and this is the perceptual aspect of that. And so the architect would bring in their plan at an early stage, and it's not as technical and it's not as focused on giving accuracy, but mostly designing or explaining to the architect based on attention, spectral masking, and A weighting, these agents. Can I understand it? Can I understand the signal, but I don't, or hear the signal, but not understand it, and therefore I'm not in the arena. So in the agent-based systems, looking at it, I focused more on the frequency aspect of the perception part, and if there is, so most of you guys are talking about controlled areas. I'm just working in like La La Land here. So the idea is, okay, so is there a background noise? Is it covering the perception of that? And then mapping it out. So most of you guys work with graphs. If you're given a graph to an architect, they won't understand anything, right? And so the idea is, okay, how do you map that onto the architectural plan for them to understand? And it needs to be fast because it's part of the design process. It's one of a million things. So I ran some multi-threading, and I limited the reflection based on the perception, not based on the other maths that come with that. And then part of the design flow, the architect decides, okay, this is the space, this is the activity that's going to be in the space. And so then there will be some attention to that. And so if the attention is focused on something else, and therefore the perception is lower, and then so then they would bring in the CAD file with their sound and the program that they're intending, like the space, what is it supposed to see or happen in there. And then it would give it then, give the architect some understanding with language that architects can understand, so plans, 3D models. Then, so that stopped for a second, and I'm moving that into a tool for architects to run in Grasshopper and stuff like that. And then we step back a little bit before the design process. So when you're going for a planning commission or you need to document the site, there is no documentation process for the site, for the soundscape of the site. So I teamed up with a music technology expert on campus, and we were trying to figure out how do we document this. But for architects, again, we don't know anything, right? He's the one that has all the cool toys, and he has the expertise, and I know how to use it. And so we tested a few things of similar to what was shown in the space, trying to record different parts of the space, and then try to see if we can create a model for the architect to understand the space. And then we thought, okay, architects, unless you're Arab Sound Lab or a bigger, big firm, you're not going to have money for like this kind of technology. And so we wanted to see, okay, what works for architects. So we looked at 360 recordings, and then we tried to see, okay, how can we work with architects and create a documentation. We also played a little bit with trying to figure out, okay, once the document is done, how are you going to experience it, and how are you going to show it to the stakeholders and to the planning commission. And so we've kind of come down to the part where we created, okay, with an iPad you can create a point cloud, and then with the 360 recording, then you just place them in place in the 3D model, and then move on from that, and that becomes a documentation like every other documentation in the process of coming up before you start designing, and then it also helps in the design process. We tested it out on a different project that doesn't have anything to do with sound, but it required a sound walk, and so everyone that you're seeing walking around really quickly are architects and designers, and they've been given different tools. Some of them were the tools that we were testing on the other project as part of the sound walk documentation, and it was part of figuring out sort of design process in a different project. And then one of the other things that I'm keep whispering in people's ears, so I'm working with a colleague that thinks about phenomenology and philosophy. How do we exist in the space? And we were looking at, okay, how do you navigate a space and collective intelligence of different things? So with the philosophy department, we did sort of an installation where we deployed some motion sensors, and it's sort of a game. So the space knows one person is in the space. Then there's a mapping between just noise and music that one of my friend's friend allowed us to use. And then if there's two, then they need to find where the music is based on the different locations, and 3, and that's the maximum. So, and then we recorded them to see how they moved through the space. It's very low tech. It was just me and him and a bunch of sensors and an Easter break. But it was pretty interesting. Obviously, the recording that I'm going to show, because we're not, we don't have the expertise that you guys have. The recording, you won't hear the camera actually canceled out the noise attenuation, but most of the people, it was interesting how to see the people move through the space, trying to figure out, okay, how do you get the music, noise. And then we moved forward and thought, okay, instead of the music, can we ask our students to think of, okay, how do you navigate a space based on binaural cues? And so they fabricated these whistles, essentially, just air pumps going through whistles, and then they deployed them in the space, but without showing anyone how to walk, and just followed how people are walking through the space to understand, can you find the path? And then the other thing that we were looking at is with the research with our master students using biomimicry and understanding, right? Can you use understanding from biological systems to create new materials? And so our student looked at bone structure, and with the impact, when you're running or walking, the bone actually starts to heat up so that it heats up your muscle. And so he thought, okay, can we use the sound from cars and out there to create an offset of the thermal heat from the outside to the inside? And so instead of using the pink insulation, we can use these types of materials. And there's also testing with different types of materials and different setups for creating personal spaces. And I think I'm gonna stop there, because I think I'm over 10 minutes already. So, sorry. Any questions?
There was a picture with someone putting something in the water.
Yes.
Sorry, I was just wondering. Because he was just under an ambisonic microphone, and I was just wondering what.
Yeah. So
it looked like he was fishing.
Yeah. Well, we were invited. Where's the picture? We were invited by a group of architects, an office that was looking for a data trust in Brixham, trying to figure out how we can document the place, and then talk to the community to figure out, because of the fishing rights now, they're moving into being more a seaside. Luke has really cool crap, and so we ended up just we recorded around the city, but then we were like, okay, let's record the water and bring that into our model. So it's going to be showcased in June. So right now we're just putting it together, but yes, it's a.
Sorry, I was just wondering.
Yeah. All right, I guess.
Thank you very much. And I'd say that you definitely are not out of place, because it's part of this initiative to have people that come from different backgrounds, which is great. Otherwise, we just get bored between us, so that we can bore someone else. Cool. Okay. I think I'm the last one because Savio emailed me saying that he couldn't attend. So, well, I'm going to tell you a little bit about an overview of a few things that we do here. Our team is called Audio Experience Design. This is actually the measurement when it was set up without the whole sphere. But in general, the activities, what we do, can be summarized in 3 separate areas. The first one is we try to understand spatial hearing mechanisms. So how do we listen to sound spatially? How do we determine the position of a sound source? We use this understanding to develop tools and numerical approaches to immersive audio, and then we apply them to well, much more applied project that might have a higher level impact. So these are the 3 areas that we work in. The main issue that we deal with in most of our project is HRTF individualization. So the fact that we have different ears, despite the fact that it's true that these are much more similar to each other than what a dog would be, actually, but still, they are different. So the main way of dealing with this, the most common way, is to measure acoustically HRTFs, which is what we do. And actually, this is a bit of advertising. Our HRTF dataset has been released. It's on a website. The paper has been accepted by the Journal of the Audio Engineering Society, but is not. They publish it only in June, so we'll need to wait for that. But they are there. We have raw, windowed, free field compensated, with minimum phase filter, whatever that means, with and without ITB. We have photogrammetry data and 3D scan of head and torso. And they're all freely available. The photogrammetry, you need to email us to get it, because it's not published, but we will send it around. But anyway, apart for acoustic measurement, what we do is to try to find ways of not having to rely on acoustic measurement. So we have this project Sonicum, which is a European-funded project with several European partners, where we're looking at different ways of dealing with this issue. Here, for example, there is an example using a parametric pinna model, similar to the work that Gavin mentioned, but in this case, he's specifically looking at the pinna. And each of those little dots, squares that you see, is a parametrizable part of the pinna that can be moved, rotated. And the idea there is that could I take a picture of the ear, extract certain morphological parameters, and then calibrate the pinna model to that, and then extract or calculate the HRTF, or take it from a data set of already calculated HRTFs. We don't do this, or maybe we are starting a bit to do this. CAT is actually starting looking at this. This is mainly being done at the Vienna, the Acoustic Research Institute, and in Sorbonne, but it's part of the same consortium. But what we are doing in trying to solve these problems, so to find the best fitting HRTF, or at least to find a full high resolution HRTF when we can't measure a high resolution one acoustically, this is a project that we are actually running at the moment, which is to use machine learning to upsample a low sample HRTF. So, well, we know that SR-GAN have been used successfully to upsample images. Why shouldn't they be able to do the same for HRTFs? So if we have very few measurements, could we upsample, create the missing HRTFs? Many people refer to this as interpolation. It is somehow interpolation, but I prefer the term upsample. So, well, the first issue is that HRTF is not an image, so how can we transform it? And this is what Aidan and some other students have done before. So trying to change the coordinate system in order to create some sort of cuboid representations, and then put them and flatten them out into 5 different squares, pad the squares in order to ensure continuity, because again, it's a sphere, and then try to use this to train GAN in this case. So to train a neural network with existing HRTFs, and then to say, okay, here I have a low resolution HRTF for which I only have 5 measurements. Can you upsample it? So that's the goal. We have a paper that we wrote and it's been submitted, and if we are lucky, in 2 years we'll be published, looking at how fast they're doing these things. But anyway, and the other thing that we have also done related to this is, can we, well, this is related to also what Gavin was saying, or what Johan was saying. Data, we need more data for HRTF training. At the moment, we're using one single data set for training our GAN, not many HRTFs available. Can we, for example, use some synthesized HRTF, for example, using mesh to HRTF, maybe lower quality ones generated relatively fast to train the lower layers of our neural network, and then reset the coefficient of the top layers and retrain them with high quality HRTFs. And this is more transfer learning, and we have something that we will be presenting at Forum Acousticum at the end of the summer on this. But to have a look a little bit of some results similar to, some results of this approach. Here we are comparing it with a barycentric interpolation, which is a very standard way, a linear interpolation between 2 points or 3 points in this case. And we also have selected 2 random, let's say, HRTFs. One is the best fitting, one is the closest one, spectrally one, the other one is a farther away one. And as you can see, when the upsampling happens between, let's say, a large number of HRTFs positioned, for example, 320 up to the full resolution, which is 1280, well, barycentric interpolation performs relatively well, the error is relatively low. But when the number of available HRTF is very low, for example 5 HRTFs, which is the minimum we can use in our approach due to our 5 sides of the cube, then barycentric interpolation starts having very high error rates, while SR-GAN performs still reasonably well. So what we're trying to do now is to further explore this, see if this improves with transfer learning, see how many less HRTFs we could use. At the moment we're using, again, we are training in machine learning using spectral data, actually just magnitude and not phase. Would that change if we use, for example, spherical harmonics in encoded HRTFs? Could we use also phase data and train the GAN with complex numbers? There's a lot of things that we are trying to look at. If anyone is interested, we have a list of things that we need to look at and only limited time. But we've also tried to assess this. This is the same thing, but just looking at all positions rather than average data. We've also tried to assess this through perceptual models, which I think is something very interesting for our domain. We know how difficult it is to run perceptual tests. We can use actually computational models that mimic human listeners, and these are some from the AMT toolbox. Specifically, the latest one is Baromerli 2022, which not only which introduced some Bayesian processing in order to really mimic how an individual will localize sound sources. So here are localization errors predicted through the model, and again we can see the same behavior where the barycentric starts going very high error rates when there is a very low number of HRTF measured, while the GAN performs still reasonably well. Anyway, this topic, this idea of using computational models, I think is a very powerful one. They don't behave exactly like perceptual tests, of course, but is a good way to narrow down the possible variables to then assess in a perceptual test, because we know how expensive and time-consuming these are to run. So we also look at various other ways of selecting an HRTF. Some are a little bit more standard. For example, we run tests where we look at how speech intelligibility improves thanks to spatial separation, cocktail party, and how these vary whether you have an HRTF that fits yours or your own, or whether you have a generic one or another person's HRTF. But this is another, a bit more long-term and blue sky approach, which is the one that I showed you in the lab, so this sphere of loudspeakers. And even in this case, our long-term approach is to try to develop a test that allows us to differentiate between different spatial audio quality, therefore possibly also different HRTFs. The idea of the mismatch negativity test, which is the one that we are borrowing from neurophysiology and apply here, is, and again, please, Kat and Andrew, tell me if I'm saying something wrong, because I'm not familiar with neurophysiology at all. But the idea, again, is you're doing a task, you have, let's say, a repeating sound like beep, 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 and then at a certain point that sound changes, like boop, beep, 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 beep. And in the EEG, you see a very clear signal after 50 repetition or 100 repetition, but still, you see something happening. Our idea is, what if we don't change, let's say, the pitch or the level of that repeating signal, but we change its position? Can we see a change? Can we see something that we can notice with the EEG? And if we do, what is the threshold? So for example, let's say that I change the position of this repeating sound. How small the change needs to be for me to still be able to observe a change? Or could I spatialize one of the repetitions with another person's HRTF? Will I see that change? So we are trying to just explore new possibilities and new ways to assessing HRTF, well, spatial audio rendering quality and resolution, which means also HRTF fit. And this is because we hate localization tests, let's face it. Localization studies are very problematic for many reasons. They're extremely tedious. After 5 minutes or even 3 minutes, you feel that you're just randomly pointing around and just saying, I want this to be finished as soon as possible. So anyway, this is part of the work we do. Another area of projects that we're looking at is at how much information do we actually need in order to compute and render a binaural scene. In this case, we look at reverberation. We all know reverberation is rather complex. We can go as, I mean, if you really want to compute, for example, with a ray tracing model, you can go as computation expenses as you want for rendering the room. What is needed? So here we have, for example, a room with a lot of objects inside and then a shoebox on the right. Which one of the two do I need to render in order to have, for example, realistic enough simulations of the room for an augmented reality interaction? And this is the sort of data that we're looking at. So on one side you have the perceived quality, the other one side you have the computational cost of the simulation. We're looking at the threshold where it doesn't make much point anymore to add resolution because we don't hear it too much. And it's similar to the work somehow you're doing with the loudspeakers. You know that at a certain point, yeah, okay, there are a few users that might be able to detect a difference, but the majority wouldn't. So this is my living room. Actually, really, we chose to model my living room. This is the high resolution ray tracing model. This is a shoebox with the same reverb time of the higher resolution model, but obviously with a different definition and much faster to process. This is the scene that we've done the test on a VR headset with a Mushra implementation. So we compare different excerpts. We have a reference and an anchor, and some of the results show again that up to a certain level it does make sense to add computational complexity. Beyond that, it doesn't. Now, obviously, in this case, I mean, this is just a very quick way of showing results. But the reference is the highest resolution. LR4 is all surfaces that have, below LR4, all surfaces that have a size of 0.4 square meters are merged together. So above this, it doesn't make much sense to change the quality because there is no significant difference. Below here, yes, there is. But anyway, the difference doesn't decay too much. But anyway, we are publishing this study, and the idea is really to see how much we can simplify the reverb, not the direct sound, but the reverb, for it to still be of good quality enough for our application. Why is this relevant? Well, this is the PPC, the Spatial Audio Forum Abbey wrote with Gavin and a few other, and here we're talking about audio production, but we also apply then this knowledge and understanding to other fields. The Bear project actually is a good one, is a good example. In that case, we use immersive virtual reality to help bilateral cochlear implantees, specifically teenagers, so teenagers with 2 cochlear implants in 2 ears. We use virtual reality to help them learn how to use both ears to perform everyday tasks. The 2 implantations are generally done at different times. Now they start doing them at the same time, but they might have big mismatch in terms of level, in terms of pitch, and so people start developing strategies which are not very positive to a certain extent. I mean, users might use 1 ear only for speech, 1 ear only for music, and what we're trying to do is to train them to use both ears together. So we use virtual reality tasks where they can be completed only by using both ears. And hoping that by completing this task more and more, they learn how to use the 2 ears together, and they can transfer this understanding from the virtual to the real domain. And then we also have a few other projects that are not really related to immersive audio directly, and I just mentioned them quickly, but we work on autonomous recording and using sound to detect and extract features or biodiversity, for example, or species count from the rainforest. Well, this is not the rainforest. Oh no, actually, this is the rainforest, sorry. We have developed a recorder. Now we are extending this to a 6-channel recorder and this will allow us to do some sort of certain type of classifications. For example, looking at, again, time of the day and location at the beginning, but then we started doing also species count and estimates of biodiversity using only the recordings, or anomaly detection, so detecting a gunshot, a chainsaw, or other things automatically. Well, very quickly, some advertising. I've done it before on the HRTF Sonicom HRTF database, but we also have our own spatializer that Johan mentioned before. Is open source, real-time, multi-platform, and it also has a hearing loss simulator and hearing aid simulator, which we are validating in a study that we'll be publishing soon. And it has a C++, but it also has a iOS, a JS wrapper, a test application, which is a standalone application, VST plugin, and also a Unity wrapper. Again, all free. And it's got a GPL version 3 license, which we're now changing to MIT, so that there is not even more problem. We had too many problems of commercial use, and also with Unity is a mess with the wrapper to have GPL licenses. And why should you use the toolkit? Well, you have a very good near field. You have a rendering individualization. You can import your your SOFA files. It has a hearing loss and a hearing aid emulation, and it is multi-platform. Now, as Johan was saying, at a certain point we start relying on work that other people have done. So I have not done any of the work that I said so far myself, but many other people have done it. This is a sort of an updated set of pictures of people that are in the lab or have left but are still collaborating with us. That's it. Do you have any questions related to any of these? I said a lot of things, but...
You spoke very fast.
Sorry?
You spoke very fast.
But I always do, so... Thanks, Gary. Yeah.
Yeah, Lorenzo, so very interested in the augmented reality study you did there with the changing the resolution of virtual acoustics. You mentioned that the reference was the highest resolution possible. Sorry, picking up on the reference. Well, I guess I wonder, had you thought about maybe doing something in the room as the reference?
We have, but we didn't at the end. So we've done some pilot tests, and initially our Mushra had as a reference the measured impulse response of the room. The problem there is that all the other excerpts were ray tracing renderings, and they sounded too different from the reference. So the problem is, if we had the reference, the real measurement as a reference, then we compacted the difference between all the others. So we've done some online tests. The test actually we've done it in two ways. One was online based, and the other one was VR. And in the online based, we had two types of references, and we decided to go for the ray tracing also for the reference sounds, simply because you would have simply squeezed the results. But your point is valid, because at the end, what we want is for the virtual sound to merge with the real one. But that has nothing to do with the resolution of our ray tracing model, but with the fact that ray tracing doesn't sound the same. I hope it makes sense. But it's a big question. When you use Mushra, what reference do you use?
Yeah, and trying to do it right as well. I mean, if it's over headphones, then considering the pass-through function of the headphones, if you're going to do that source of the real world, that's probably the problem.
But you have, there are so many variables there. But at least, I mean, if you have that, if you use ray tracing, then it could be informative. I'd be happy to send. We submitted the paper a month ago. I'd be happy to send you the results and also the audio excerpts, which are quite interesting. Because not only we reduced the spatial resolution, but we also did another test where we reduced the number of frequency bands in the absorption coefficients. So we started from 8, then 4, then 2, and then 1. And it's interesting because in that case, it influences much more what you hear. Up down to 4 is okay, but 2, no, you hear it, and it's not good enough. Getting.
On a comment, I did a reverb test, an actual test, a very similar amount of 2 months ago, had the exact same thing with reference. We compared some conversations between the real and use code. Yeah. My question to that is, in your tuning kit, how are you doing near field source material?
Oh, no, go.
No, I was going to say,
we simply calculate, we use I think we use the wave equation, the one from Algazi and Duda for a snowman model, and the 2 years on the sides. And what we do is we know that the HRTF has been measured, or you can set at which distance the HRTF has been measured. And so we calculate we simplify with I think it's 4 biquads, 4 cascaded biquad filters per year. And we calculate what would be the difference between the distance at which the HRTF has been measured and the distance where you want to render. We take the coefficients from a lookup table that has been pre-calculated. So it's simply 4 biquads per year. And what they effectively do, they increase the high frequency interaural level differences the closer the sound source gets.
You don't get a low frequency boost? That's what I mean. Get an infrared.
The main thing is we decrease the level difference between the two. Well, they increase the level difference at high frequency. Probably there is also a low frequency boost. I don't know, we use that equation. But the main thing is that you have bigger interaural differences at mid to high frequencies for near field. And then we also change the parallax. So the acoustic parallax, so we just pick an HRTF independently from each ear. And obviously the signal to noise ratio, but that's, so the reverb increases at plus 3 dB every doubling, and the sound direct path is plus 6.
You do that,
Yeah. And at the moment we have, I think in our new release we have an image source reverb and a convolution-based reverb, but we also implemented SDNs from Enzo de Sena, but we can't release it because it's not ours. but I'm sure that if you want, then we can ask and you can get it. But this is scattering delay network, is a sort of a simplified image source. Yeah. Brilliant. So, I was the last one of the day. I guess, I mean, we don't need to chat more. We can go to a pub to have a drink. But the idea is, well, the idea of this meeting was first to do a first in-person meeting of SIG. And there are two things that I'd like to put out. First is there anyone interested potentially in being more active in the activities we organize and in what we do? And if you are, you don't need to tell me now, but just drop me an email later. At the moment, it's been mainly myself and Aidan organizing things, and there is Filippo, but Filippo tends to be very busy. So it's mainly me and Aidan. But anyway.
He's busy at the Z today.
Sorry?
He's busy at the Z today.
Yeah. Well, also he had a new kid now, so of course he's busy. But anyway, Filippo, we meet regularly. But if anyone is interested, then please do let me know. And the second thing is, what activities could we do? I mean, so far we have done a workshop on soundscapes, which worked very well. And this was last year, but it wasn't specific on immersive audio, but it worked well. We have done a day where we visited L Acoustics, which was amazing. I really loved it. They had very comfortable chairs. I don't know if I've ever been at their demo room, but it's amazing. It's very comfortable. That was great. We can redo that. Now, we had Sonos today, which was amazing and very good. We are going to organize, we're going to host here the Basic Auditory Science Conference in September. But again, it's not specifically spatial audio, it's mainly on auditory science. What are things that we could do? And we don't need to say it now, but what could we do? What would be interesting? I mean, even just presenting things, I guess, I saw people taking pictures, so I guess maybe there's going to be some follow-ups. But is there something that you think we could do to use these resources? And resources, I mean that we also have some money that we can use. Not much, but I'm sure we have good ideas. We can ask for more. The UK Acoustic Network has got money, so and we actually have money from other projects, so we can definitely organize things. What would be useful to do? And here, maybe I'm also thinking about early career researchers, PhD students, postdocs. Is there something that would be nice to do? For example, we keep talking about tools. Johan, for example, is organizing a workshop at the AAS conference.
I proposed it. It's not guaranteed that it will be accepted.
Well, Gavin is here. It's gonna put
the workshops.
But he's got. No, I'm sorry, I'm joking. Of course.
Accepted on the strength of a proposal. Nothing else.
But for example, we talk about the toolkit. We could run a workshop where we present not only that, but maybe some tool where we show how these tools can be used. This could be useful for early career researchers.
I feel like a careers one would be quite useful because I feel like there's a lot of industry and academic tie-ins, and I guess at least the previous field I was working in, there wasn't much movement, or at least I didn't get exposed to much movement from academia to industry, or even if people go from industry to academia. I don't know, like a bit more of a general talk between the two groups. I think would be quite good.
Yeah, I agree. And this is, I mean, this is why I think visiting L Acoustics was great. The Sonos is here is great. What could we do? I mean, visits to companies?
So there's basically a bunch of groups who all do cool research, including VR and life don't get the impression of what it actually sounds like. So could you put some money into hiring a venue with several rooms and basically having a standalone demo day where you invite industry to come and actually experience some of these things for real? And but go wider, like NHI, HR are sponsoring research here, so they get them in people and get fairs, events and things. So we always talk to ourselves because we're from technology, but I think we need to talk to the wider academic and kind of industry and get UPRI involved and actually say like there's some really amazing stuff going on and what you can do with like autism is something that we should be doing a lot more. So like make it more focused on the application and what you can do with it rather than the isn't it great that we can talk about HRTS and stuff like that.
Yeah, absolutely. I mean, we are going to the Royal Society Summer Exhibition, Summer Show,
Yeah,
but only as a group
and
demonstrate.
That's one group.
No, exactly.
Targeting the public.
Exactly.
Maybe it should be lots of groups targeting people who could actually buy into it.
Yeah. Yeah. No, I fully agree. It would be nice to have an event where we look at what demonstrations we have that are demonstrable, I'd say, because not everything is, and get a venue, or even here. I mean, but we could get a venue and invite all these people.
I guess you need enough space and enough acoustic isolation that you can do demos without people interfering, with the neighbouring demo. And it's time to set it up properly as well. Like if it's a rush job, then it's going to be crap.
Well, a university in the summer. That would be a good thing.
Yeah, definitely.
For you as an architect, you know how to acoustically isolate spaces.
But yeah, I mean, yes, I think that's definitely a good idea. Anyone? Well, no, the thing is, these things, either there is someone who organizes it, or we pay someone to organize it, or, yeah.
I think my perception is for academics to invest the time into doing a good demo. There needs to be a payback, there needs to be a reason for doing it. And obviously, showing that you don't EPI is good, but actually the chance of having follow-on projects or funding from it is why you would do it. So I think it's committing to kind of actually getting the people to come and listen who aren't kind of interested but could actually use it.
I mean, I've recently given a presentation at the for example, the Cystic Fibrosis Trust, because they funded a small project on hearing monitoring using VR, because cystic fibrosis patients often take antibiotics that are ototoxic. And so we gave them an Oculus Quest and they do their test. And I found it amazing because no one knew about anything of this. And I brought an Oculus and they tried it. And it was very fun. And they learned a lot.
Promoting that to a wider audience.
Yeah, of course. That would be nice.
And the digital catapult, this new used to what who are they? Is a group that's promoting virtual reality, immersive stuff.
Is it Immerse UK?
Yeah, maybe.
It's part of the catapult, yeah.
I mean, it might be doing something in collaboration with them.
Yeah, they cost money. No, but is anyone working with Immerse UK? I received their newsletters, but I've never done anything. Just to become a member,
Yeah, like the first year was free, it's great, and then they started charging for it.
Yeah, no, exactly. But yeah, but no, I mean, definitely, I mean, by putting together our knowledge and our links, well, it's a big effort. Not only we need to think what demos are available, and then what venue, and then what dates and whom we can invite. So it's a good effort, but yeah, I can chat about it with because that's the problem a bit. Who can lead on an activity like this? Which, I mean, I do agree that it would be great. Anything else? Okay. Would you be happy to do something similar to this every year, in general?
Yeah.
Maybe more people will come. Okay. Cool. Then I think we can stop it here, and we'll send. I mean, the video will put it on the website, but yeah, and then we'll follow up via that you can SIG mailing list and see if any of these activities could be explored further, and maybe think about other industry visits. Brilliant. Thank you. And should we go? Who is up to go for a drink?